Hello everyone, my name is Ayush Patre and today I am going to explain you topic diffusion into a falling liquid film which is gas absorption. So here we are going to study how a gas get absorbed into a liquid film which is flowing downward under gravity. So we are considering here a gas A has been absorbed into a liquid B and we are assuming it has a laminar flow. The flow is laminar and the liquid forms a thin falling film and the diffusion is very slow. The diffusion is taking very slow in the liquid film so that the A will not penetrate very far into the film. So this means that the gas will not go deep into a liquid and the most mass transfer happen near the surface. So we are considering here the cell bands approach for our derivation, and we are assuming a Cartesian coordinate system which is XYZ. I have given the orientation here, so you can see the velocity will always be in the Z direction, and we are neglecting the velocity in X and Y direction because it is a laminar flow as our assumption states that, and the Vz is only the function of X. It is not a function of Y and Z because we neglected the end effects and due to continuity equation, and Vz is a function of X because the velocity varies only with the direction from the interface and we are assuming it has a steady state operation. And from momentum balance velocity profile of Vzx, we know the equation and we will use it later. And now we will go for a mass balance for our cell and we are considering a stationary differential volume cell of dimension delta x, delta z and w, which is given in the figure delta x, delta z and w. And we are considering it as a differential volume cell. Now we will use a conservation of mass for species A, which is rate of A in minus rate of A out plus rate of production equals to 0. Assuming no chemical reaction in steady state and we will get our equation like this, and after that we are dividing it by w into delta x into delta z and taking the limit as delta x comma delta z tends to 0 we get this small equation from this, and later we will use a flux expression which means using a fixed first law for the x direction and deleting diffusion the z direction, which is nax equals to minus dab into del ca by del x and naz equals to vz into ca. We will use the two equations, substitute in above equation and we will get this small equation which is our main equation. Now we are going for a boundary condition. First boundary condition is at x equals to z, at z equals to 0, c equals to 0, which means at x equals to 0, at z equals 0, which this one, the pure liquid enters. So at x, z equals 0, our c equals to 0. And second boundary condition is that at x equals to 0, c equals to c naught. At x equals to 0, which is this, our c equals to c naught. We are which means the liquid surface is in equilibrium with the gas. And third boundary condition is the wall is impermeable. The x equals to delta, the wall is impermeable. So at x equals to delta, this is a wall. So at x equals to delta, del Ca by del x equals to 0. Now we are using analytical solution for our short time contact for short films where the gas only penetrates the near surface, where which near surface means x is near about 0. Our our vz is near about vx max, so we will put vzx as v max and we will get this equation, and from this and we are integrating and we will integrate this and we will get this big equation of c upon c naught. After that, to find the local and total mass transfer, we will use this equation, and and we will get a total molar flow rate wa over length l and width w, and we will get this equation, this main equation. For second, we'll use the equation of change approach. We know the general equation of change for component A is del Ca by del T plus Vx into del Ca by del X plus Vy del Ca by dy plus Vz del Ca by dz equals to dAb, and this equation plus R. Here we are using some assumption and simplification. As steady state, we are considering a steady state del C by del T equals to 0. We are considering the laminar flow, which means Vx equals to 0 and Vy equals to 0, negligible the end effect. That's why we are neglecting Vz as a function of Y and Z. And we are considering no chemical reactions. Ra equals to 0, and axial diffusion is negligible. And our equation, which is this equation, get reduced to this equation where Vz is the velocity of liquid film in z direction, C is the molar concentration, del C by del Z is the concentration gradient, D with diffusivity of A in B, and del square C upon del X square is the curvature of concentration profile. And from and the boundary conditions are the same and results are the same. The numeric problem is on topic the chlorine absorption in a weighted wall tower. The question is the chlorine absorption in a falling film, which is given in figure 2. This is the figure 2 assessment diagram of a weighted wall column. The chlorine is being absorbed from a gas in a small experimental weighted tower as shown in the figure. The absorbing fluid is water, which is moving with an average velocity of 17.7 centimeter per second. What is the absorption rate in gram mole per hour if the liquid phase diffusivity of the chlorine water system is given and if the saturation concentration of chlorine in water is given per 100 gram water? And these are the experimental value at 16 degree. The dimension of the column are given in the figure. Ignore the chemical reaction between chlorine and water. So given data is tower length 13 centimeter, tower radius which is given, and we can calculate the weight as we are given the cylinder. So it width will be 2 pi r. The average velocity V average is given 17.7 centimeter per second. We can calculate the Vmax as we know the formula Vmax equals to 3 by 2 of V average, and divisibility we had given in the question is our figure, our length, radius, chlorine bearing gas is coming from downward, and film thickness del is given, surface concentration assume equal to saturation concentration, and the water film runs down the wall. The saturation concentration CN0 is also given 100 gram of H2O. Now first we will convert the concentration to the molar unit using the density, and since density is not giving, we are assuming density has 1 gram per centimeter cube, which is equivalent to 1000 kg per meter cube. So CA0 we are converting in gram mole per centimeter cube here, and after that we are calculating the molar absorption rate, which is WA, and we will use this form. We can get this formula WA from our derivation, which is this formula, and we will use this and we put all the values as we know all the values WL, CA0, DAB, Vmax, and L. Everything we will put here, and we will get a WA, and we will get it as a gram mole per second, and we will convert it into gram moles per hour by just multiplying 3600 in it, and we will get the absorption rate as 0.7273 gram moles per hour. Now we will go for our fourth numerical, fourth question, the exit concentration calculation. Here we are using the same question, but here it asks the chlorine water system describing question 3. Calculate the average molar concentration of chlorine Ca in the liquid film at the exit of the column Z equals to L. At exit of the column Z equals to L, we have to calculate the average molar concentration, and the film thickness is there determined to be 0.05, which is given. The film thickness is given, there total molar flow rate we are calculated from our question with 2 pi r, and average velocity we know. So we know the relationship between total flow and average concentration has this, which is the W equals to double integration 0 to W 0 to del Vz into Ca into dx dy equals to W del V average of Ca. So we will solve for the Ca, and which is and rearrange the formula, and we will get Ca average of Ca equals to Va upon Wa upon W into del into V average. So we will substitute all the value, we know all the value Wa, W del, and V average, and we will substitute all the values here, and then we will get this average concentration at Z equals to L. So, thank you.